Hey everyone, and welcome to this explainer. Okay, today we are taking on a topic that, let's be honest, often strikes a fair bit of fear into the hearts of calculus students everywhere. Multivariable functions. But I promise you, by the time we wrap up here today, we're going to completely change how you see them. We are going to take all those intimidating abstract numbers and treat them as what they really, truly are, actual physical landscapes. So grab your gear because we are going to go out and explore the geometry of math.
Look, if you're a student who's been, pulling your hair out trying to memorize formulas for intersecting planes, curving surfaces, and directional gradients, I just want you to take a deep breath. I know, staring at these 3D equations feels like looking at a scrambled code. So let's just close the textbook for a second and go for a hike. Seriously. We're going to step completely away from the abstract algebra and focus entirely on visual, geometric intuition. You absolutely don't need to be a human calculator for this, you just need to be an explorer.
I want you to keep this one central question in the back of your mind as we journey forward today. What if these complex, multivariable equations are simply maps of mountains? Because when you see an equation with an x, a y, and a z, you aren't just looking at a math problem on a page, you're actually looking at highly specific topographical instructions. Think of it like this. Your x and y are just your coordinates on the ground, and your z, that's just telling you how high up the mountain you're standing.
To put that into perspective, check out this absolutely breathtaking shot of Half Dome in Yosemite National Park on the left. It's this massive, physical, three-dimensional piece of solid granite, right? Now, look over on the right. That is its exact mathematical translation, a two-dimensional topographic map. Every single ridge, every valley, every sheer cliff face of that real-world mountain is perfectly captured right there in those flat lines. It just brilliantly grounds our math in reality.
But here's the secret. To understand the whole mountain, we have to look at it one elevation level at a time. And honestly, this is the absolute big secret of multivariable calculus. We don't try to swallow the entire 3D space at once. I mean, our human brains just aren't naturally wired to process that. Instead, we break the complex shape down into flat, horizontal slices that we can actually digest.
Okay, let's dive into this with our first practice hill. What we have here is a three-dimensional hemisphere sitting on an XYZ plane. That flat ground right beneath it, the grid, is our X and Y plane. It's exactly like a paper map resting flat on a table. And that vertical Z-axis pointing straight up into the air, that is our altitude. So we are going to climb this mathematical hill together, step by step.
So how do we actually create those map lines we saw earlier? Well, mathematicians do this by finding what they call level curves, and it is a super straightforward three-step process. First, you just pick a specific altitude on your z-axis, let's say 100 feet up. Second, imagine taking a massive sword and slicing horizontally straight through the hill at that exact height. And third, you just look at the shape of the cut and trace the resulting ring. It's that simple.
Now, what's really cool about this is how repeating that slicing process creates a totally navigable map. If you look on the left, you can see all those individual horizontal slices collapsed straight down onto our flat map, making these concentric rings. Each ring represents a totally different altitude. It's actually a lot like reading isotherms on a weather map. Every point on a single ring means you are standing at the exact same elevation. And on the right, you can see how this exact same concept scales up to map things like temperature or pressure inside solid 3D objects, which creates these awesome level surfaces.
All right, here is your golden rule of thumb for your mathematical hike. And the best part is, you don't need a single complex formula to use it. Ready? Close together lines mean a steeper climb. Space them out, and it's a gentle walk. If you're looking at your contour map and the rings are packed super tightly together, you are basically staring at a cliff face where the altitude is changing super fast over a really short distance. But if there's wide, open space between the lines, you're just strolling comfortably through a flat meadow. Now, obviously, not every math mountain is a perfectly smooth, simple little dome. Just look at the incredible diversity of these mathematical landscapes. We've got sharp, sweeping peaks, we've got rippling waves, and we even have what mathematicians literally call saddles, which, as you can see, look exactly like a horse saddle or a mountain pass dipping right between two peaks. And the key takeaway here is that every single unique surface shape creates a completely different, unique contour map right below it.
So, let's talk about the actual hike itself. Imagine you were standing on the side of one of those wavy mountains. Your steepness, your slope, depends entirely on which way you choose to face. Facing east, moving strictly along the x-axis, might be a totally gentle downhill walk. But if you pivot on your heel to face north, moving along the y-axis, you might suddenly be staring straight up a severe vertical incline. So the crucial point here is that in 3D space, slope is no longer just one single number like it was back in basic algebra. Take a look at this curved paraboloid surface. If we stand at a specific coordinate and lock our compass to step exactly in the x direction, we get one specific steepness, which you can see highlighted there resting on the curve. That represents your slope. But if we reset and step exactly in the y direction, we get a totally different steepness. Your slope completely changes based on your heading.
Okay, and here is absolutely the best part of our hike today. I want to demystify a frankly terrifying piece of jargon for you. Measuring steepness while facing strictly one compass direction is all a partial derivative actually is. Seriously. When your textbook asks you to calculate a partial derivative with respect to x, it is simply asking, hey, how steep is the trail if I walk exactly east? It's just a directional slope. Nothing more, nothing less. Let's just take a quick pause at this rest stop and review the rules of our math trail so far. First, every coordinate on our map dictates a specific altitude on the surface. Second, slopes change entirely based on your compass direction. And third, and this leads us right to our grand finale, from any given point on the side of the mountain, there is always one singular, absolute, steepest path to the summit.
And that brings us to the ultimate tool for going off trail, the gradient. Let's strip away all the dense algebra for a second and just focus on the physical meaning here. The gradient is simply the exact compass heading that points you straight up the absolute steepest part of the mountain. Think of it as an arrow sitting flat on your 2D map telling you, hey, if you want the hardest workout and the fastest way to the top, walk exactly this way. Or, to look at it another way, if you were to drop a ball right at your feet, the gradient is the exact opposite of the path it would naturally roll down.
And this brilliantly illustrates exactly what we mean. If you look at the bottom plane here, see that red vector arrow lying completely flat on the grid, pointing out from our starting coordinate? That right there is the gradient. It lives down on the flat map, but it mathematically calculates the shape of the 3D bowl above it, and it points you directly in the direction of maximum increase. It is literally your ultimate mathematical compass.
So we've successfully reached the summit of our hike today, and I really want to leave you with this final, somewhat provocative thought. The next time you open a textbook and look at a complex multivariable equation, are you just going to see a scramble of abstract numbers? Or will you see a brand new, beautiful landscape just waiting to be explored? Thank you so much for joining me on this explainer. Keep visualizing, keep hiking those math trails, and I'll catch you next time.